So I'm going to talk about polar nonpolar molecules, and uh, the idea is that, for example, if I were to draw this molecule, all right, um, I'd sit there and go just to review. I'd go 4 plus 4 times 1, counting up the valence electrons. So I'm going to get 8 valence electrons. The stick figure would put the carbon in the middle, connected with the 4 hydrogens this way. I would be achieving a stable octet with the carbon, and the hydrogen is happy with 2. Okay? So when I look at this, there's going to be an even distribution of electrons around that molecule. And when you sort of have this even distribution, it's considered to be nonpolar. Now, I'm going to compare that now to a molecule that is polar. And what I'm going to draw is a water molecule. So again, to reinforce the whole deal, I got 2 valence electrons for the hydrogen, I have 6 for the oxygen. Again, I have 8 valence electrons. I would connect hydrogens to the oxygen this way. That would take out 4 electrons, leaving 4 left over, and I'd put them this way. Well, when you drew this molecule, H2O, or you made a model of it, it ended up looking more like this. And we called that a bent molecule. Well, that's very important because being a bent molecule, it is going to be polar. And what I mean by polar is, when I look at this molecule, I'll get rid of this orientation of it and all this, okay? I can sit there and I can say, all right, I have a really high density of electrons on one side of it. That density of electrons imposes sort of a partial negative charge. And now, when I have a partial negative charge, it induces a partial positive charge on the other side. So I end up with this sort of like a big bar magnet, a negative side and a positive side. That is called a dipole. And if a molecule has a dipole, or a dipole moment, it is going to be called, or it is going to, from that point on, be polar. Now looking back up at this nonpolar example, yeah, there's some electrons here, some here, some here, some here. And you know that when you put them all together, you ended up with a tetrahedron. But the point is, it's an even, there's no way I can say, yeah, I have a higher density of positives here and negatives there, whatever. That can't happen with this molecule. So it sort of happens through inspection. Now here's another example. Take sulfur trioxide. I'm going to draw this molecule. Okay, I got 6 for the sulfur, I got 18 for that, I end up with 24. I have a skeleton that looks like this. I start putting the, subtract 6 out of that, and that leaves 18, and I go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and I step back and go, ooh, wait a second. The sulfur in the middle, right here, he only has 6, no big deal. I'm going to take 2 of those non-bonding electrons, kick them over into a bonding position. When I do that, I end up with a double bond to the sulfur. Sulfur now has 2, 4, 6, 8. Everything's happy. Looking at this molecule, all right, I have taken as a whole an even distribution of electrons. For the most part, there is no one side that has more molecules or more electrons than the other side. So this would also be considered nonpolar. So a lot of times symmetry, the fact that it's kind of symmetrical like this, really plays a big part in determining whether a molecule is nonpolar or polar. Right? Here's another one. Let me erase this. Okay, this time, this one will be a little trickier because I'm going to go through a series of carbon chlorine compounds. First one I'm going to do is CCl4, carbon tetrachloride. Then I'll do CCl2, CCl, better put an H2 on that to fill it out. That doesn't even look like a C. CCl H3, something like this. Alright, so for the first one, carbon, 4 chlorines, looking like this. Every chlorine has 6 valence electrons around it, looking like this. If I take that as a whole, there's no way I can say one side is positive, one side is negative. That's nonpolar. Now the next one, carbon in the middle. Now this one I got to be kind of careful on because it depends on how I draw it. So I'll draw it the way that looks nonpolar. 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. But you got to be smarter than that because you got to realize that this is a tetrahedron. That shape right there is a tetrahedron. And in reality, it sort of looks more like the carbon. You have a hydrogen on one side, you have another hydrogen going back, then you end up with the chlorine and the chlorine down here. Well, as soon as I did that, realized that that tetrahedron in reality looked like this down here, boom, I've got another dipole. Negative side, positive. Huge distribution of negatives on that side of the molecule, inducing a positive, partial positive charge on the other side. So that's a dipole. Alright? The last one, I'd sit there and go, okay, carbon, chlorine, 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 hydrogen. The chlorines all have 6 electrons around them. And again, if I look at that, take it as a whole, the whole thing, I've got negatives, negatives, negatives. I've got a basic imbalance. This one would also be polar because I'm going to sort of have a negative side and a positive side. Alright? Not very polar. This one's probably not very polar. Not as polar as this one, but it still is polar. So I ended up with a polar molecule. This was polar, and this was non-polar. Oops. Better spell polar right. Alright? We'll work on these in class.